Alkanes can adopt a variety of conformations because single bonds, or sigma bonds, can rotate freely. Depending on how these bonds are rotated, you can have changes in energetic stability. So we're eventually going to build up to how these two conformations of butane are different and why we draw it like this typically. But before we can do that, we need to take a look at a simpler example. Let's take a look at ethane, C2H6. We would typically draw it like this. You can see the same zigzag pattern as in the example above, only we're using two hydrogen atoms here and here instead of carbon atoms. Let's begin to rotate this. We're going to take this rightmost carbon and we're going to begin rotating it towards you. So it's starting to look like this. As we complete the rotation, it's going to look like this, where the back carbon atom is actually hidden behind the front carbon. We can identify which hydrogen atoms are associated with the front carbon, this one, and this one, and the other three are attributed to the back carbon. So what happens is we begin to spin and rotate along this bond. So we're going to replace the top hydrogen atom with a gray atom, just so we can keep track of it. And notice I shifted the angle a little bit so that you can see the back carbon peeking out. So let's take this hydrogen and we're going to rotate it 60 degrees clockwise. What happens is we get a change in the way the hydrogen atoms are aligned. The front hydrogen atoms are now very close to the back hydrogen atoms, where before there was a decent distance between the two. As we rotate this another 60 degrees, we get back to a conformation where there's a distance between the hydrogen atoms. Rotate again. We have another conformation where the hydrogens are very close to each other, separate, and close. Each time we're rotating 60 degrees. Now, it's a lot of work to put together these types of structures, and obviously you can't do that on paper. So what we're going to do instead is do something called a Newman projection. A Newman projection is a simplified way of drawing these conformations. And if we rotate the Newman projection, we can figure out how the energy changes as that central bond between the two carbon atoms rotates. So in a Newman projection, we're going to start with the frontmost carbon. So in this case, it's these three atoms here, or these three bonds. Okay, we're just going to draw a shape just like that. Each of these are 120 degrees apart. We have a hydrogen atom on each of these. Now for our back carbon, by convention, what we do is we draw a circle. The back carbon has a shape opposite. So we've got a hydrogen down here, a hydrogen up here, and a hydrogen up here. So this point here is the front, the larger circle is the back. Okay, how do we draw this conformation? Again, we're going to take the front and we're going to look at its structure. Notice we've moved that one hydrogen over to the right. So this hydrogen was originally up here, now it's over to the right. The back hydrogens don't really change. We're going to draw them a little bit off-centered so that we can see them. They're not exactly behind because we just can't draw it that way. Okay, we have these two different conformations. Again, this Newman projection symbolizes how we're rotating the bonds in our actual molecule. When the hydrogen atoms are separated like this, we call this a staggered conformation. When the hydrogen atoms are close to each other, as in this case, we call that eclipsed. And as you saw in the previous slide, as we rotate around, we alternate between staggered and eclipsed conformations. We can map the energy of this if we know the energetic penalty for an eclipsed interaction. We know that for every two hydrogen atoms that are eclipsed, there's a 4 kilojoule per mole energetic penalty. I don't care if you memorize that number, we can look it up. So let's go through and let's draw all of the different conformations, starting with the first one. So if you remember, the first conformation we had looked like this. And we would assign this conformation as a staggered conformation. If it's staggered, it's our lowest energy state. These are relative energies, so we're going to put 0-degree rotation. Our relative energy is 0. As we rotate 60 degrees, you can rotate the front or the back. I'm going to hold the back constant in this example, but you could do either one. I'm going to underline the hydrogen that you should focus on. As that rotates 60 degrees, it ends up in an eclipsed conformation. Again, that's this hydrogen here. We have 3 pairs of eclipsed hydrogens, so the energy jumps up to 12. As we rotate again, we're going to hold the back hydrogens the same place. We're going to relax from this eclipsed conformation where there's a lot of strain, and we're going to end up with a new staggered conformation, back to a 0 energy state. And we can keep drawing this all the way around where the hydrogen moves, but in the case of ethane, it's going to alternate from staggered to eclipsed each time. The higher energy being eclipsed, and the lower energies being staggered. As we connect these together, you get this nice curve. So what happens if we look at a different molecule? In this case, let's take a look at propane instead of butane. So we would typically draw propane like this. In this example, we have to choose which carbons we're going to look down. I'm going to say, arbitrarily, we're going to look down the 1 and the 2 carbon. So let's draw a little eyeball. The eyeball is looking straight in the plane of the screen here, and we're looking at the carbon, the 1-2 carbon axis. So let's draw in the extra hydrogens just to be really clear. There's one coming up towards you, one going back. In this example, we have one up, one down, and one down the other way. So now we're going to spin this towards us, and let's draw the first Newman projection of this. If we spin it towards us, the 1 carbon has a hydrogen pointing up, one to the left, and one to the right. The back carbon has a hydrogen up to the left, up to the right, and instead of a hydrogen on the bottom, we have this methyl group right here. So we can write a CH3. I'm going to write Me, which is the abbreviation for methyl. This is going to be our lowest energy state because we don't have any eclipsed interactions. So that's going to be 0. We can rotate either one. I'm going to rotate the back this time, just so we do something a little bit differently. We're going to highlight that hydrogen. We're going to keep the front atoms the same. So the front carbon has 3 hydrogens. The back carbon, we've rotated 60 degrees, so this hydrogen is now eclipsed. The methyl group is now eclipsed, and this other hydrogen is now eclipsed. So let's compare the energies here. We have 2 eclipsed hydrogens, so that's 4 and 4, gives us 8. But since a methyl group is larger than a hydrogen, there's more energetic strain associated with this eclipsed conformation. In this case, 50% more, 6 kilojoules. So that's this interaction here. So 6 plus 4 gives us 14. Again, we're going to keep the front carbon in place. We're going to rotate another 60 degrees. Another 60 degrees will relax us from an eclipsed conformation to a staggered conformation. Our methyl group moves up here. Our hydrogen that is underlined ends up here. And our other hydrogen is here. You can see that we have another staggered conformation where there's no eclipsing of the atoms. That takes us back to our lowest energy. If you continue to spin around, you can draw all the other Newman projections in practice, but the energies are the same. So this should look very similar to the original, what we did with the ethane, except this energy is a little bit higher because of our eclipsed conformation with the methyl group.